In this problem, we are trying to estimate or approximate a definite integral using something called the midpoint rule. And if you've done Riemann sums before, this should be very familiar. So here's our integral here. This big, long, stretched out curly thing is our integration sign. And then it's definite because we have a beginning point and an end point. So we're looking at some curve on a graph from -3 up to 3. And we don't know what the curve does. This is a rational function, so probably it's going to go all wacky all over the place. But let's just draw in a pretend curve. And the process here is to split the area in this interval up into rectangles and get an approximation for the area under the curve by summing up the areas of all the rectangles that you make. In this case, we're not going to use the left-hand border because it's probably going to be an underestimate or maybe an overestimate depending on which way the slope of the graph is going. And we're not going to use the right-hand endpoint of the rectangle, which would make that rectangle. We're going to use the midpoint. So we're going to find the middle point and get between them. So if one of those, the left hand or the right hand, is an overestimate always, and one of them is an underestimate always, the midpoint is probably going to be better. And that's the theory behind using the midpoint rule. Otherwise, it's just the same as doing a Riemann sum. What we need to do first is figure out how many rectangles we're going to have and then where the midpoints of those rectangles are going to be. So we want 4 subintervals, it says, and we want to use the midpoint rule. So let's see, we're going from -3 to 3. That's 6. So a rectangle is going to be 1.5 across, because 1.5 plus 1.5 is 3, and then another 1.5 and 1.5 is another 3, and that's 6. So there we go. So here we are right here at the point -1.5. Here's the point +1.5. The midpoints then of these rectangles, well, halfway between -3 and -1.5 is -2.25. Halfway between -1.5 and 0 is -0.75. And then we're going to have a mirror image of that on the other side. We're going to have +0.75 and +2.25. So those are our endpoints. The width of all these things is 1.5. And what we'll do is we'll take these midpoints, plug them into the function in order to get the height of that rectangle and multiply it by 1.5, the width, and then add them all together. I think the easiest way to do that is with a spreadsheet. So I'm going to do that. So let's go ahead and put in our midpoints. We had -2.25. We had -0.75. We had 0.75. And we had 2.25. Okay, so those are our midpoints. The height is going to be the formula of the function evaluated at that midpoint. So let me remind myself what the function is here. We've got t minus 7 over 5 minus t. Okay, so I'm going to type in a formula for this. Start with the equal sign, and then I'm going to do 2 sets of parentheses with the division symbol in between. And we've got t minus 7, except it's not t. What we want is this minus 7, and then on the bottom, 5 minus that. Let me just double check that I actually, well, let's go ahead and fill down. Double check that I actually got that right. T minus 7 and 5 minus t. Yep, that looks good. Okay, so now the width for all of these is 1.5. And the area is just going to be the height times the width. So we'll put an equal sign again and click that for the height, and then the multiply sign, and that for the width. And we'll go ahead and fill down. So those are all the areas of my rectangles. It looks like we're below the x-axis because those are all negative. And then we just need to sum those up. So equals sum, and select those, close parentheses. And there we go. We got 8.7323. I think in these they want 4 decimal places. So 8.7323 is going to be the answer for that one. So that's how to approximate a definite integral using that midpoint rule.